Welcome to this explainer brought to you by Forge College. Today, we're bridging the gap from our last lesson, Why Account Models Matter. We're finally tackling that huge multi-million-dollar question, how do you actually port your EVM smart contracts over to the SVM without breaking absolutely everything? If you've spent any real time building on Ethereum, your brain is fundamentally wired for one very specific way of managing state. Well, today we are completely rewiring that circuitry.
Here is our architectural blueprint for today. We'll be hitting the state mapping bridge, cabinets versus mailboxes, storage versus account data, a real-world primitive mapping cheat sheet, upgrades and migrations, and we'll wrap it all up with some key heuristics.
All right, let's dive right into Section 1, the state mapping bridge, moving from EVM to SVM.
Now, making the jump to the SVM sounds incredible in theory, right? But obviously, you can't just copy-paste your Solidity code, convert it to Rust, and pray it works. It doesn't work like that. You need concrete, actionable mappings to restructure your architecture. Where Ethereum hides state as this opaque internal memory region that's permanently glued to a contract, Solana does the exact opposite. It exposes state explicitly as totally separate, discrete on-chain objects. Think of it this way. On Ethereum, the contract is essentially a monarch holding all the cards. But on Solana, the data accounts are the actual entities, and the programs, they're just authorized actors interacting with them.
Moving on to Section 2, cabinets versus mailboxes. Let's ground this in a really concrete metaphor. To make this complex architectural shift feel super intuitive, I want you to picture an Ethereum smart contract as a massive, heavy, locked filing cabinet. Absolutely all of your documents, your balances, your mappings, your arrays, they are all stuffed inside this one box, and only the contract-specific code holds the key to open it. So if a user wants to update their balance, they basically have to wait in a single file line, the contract unlocks the cabinet, edits the file, and then locks it right back up. Sure, it's safe and atomic, but what happens if a million people want to use it at the exact same time to mint the latest meme coin? You've got yourself a massive network clogging bottleneck.
Now, conversely, I want you to map Solana to a huge wall of distributed mailboxes in a giant apartment complex. Each mailbox is a totally separate account. It has a fixed physical capacity and a very explicit owner stamp right on the front. In this model, Solana programs aren't filing cabinets at all. They're just postal workers, and a postal worker can only open a specific box if that owner stamp explicitly grants them permission. The massive benefit here? 10 different postal workers can open 10 different mailboxes at the exact same time. And that right there is the secret sauce to Solana's incredible parallel execution.
Section 3, storage versus account data. Let's map this physical metaphor directly onto the tech. Over on Ethereum, you've got these rigid 32-byte storage slots that the compiler just implicitly manages for you. You don't really have to think about data at the byte level, because Solidity handles the heavy lifting behind the scenes. It's kind of like that one senior dev who never writes documentation, but somehow keeps the whole back end running smoothly. But on Solana, no magic happening behind the curtain. You have to explicitly design a serialization layout, run your data through a serializer, like Borscht, for example, and store it explicitly inside a data buffer.
And this level of explicitness carries some huge implications. Because Solana accounts have explicit byte sizes, and because you quite literally have to pay rent in Sol to keep them alive on-chain, you are forced to consciously choose your architecture. Do you pack all your user data into one giant mailbox, or do you shard it across thousands of smaller individual ones? Plus, your write authority is completely separated. It's a strict, explicit opt-in model, which is a big departure from Ethereum's intrinsic rules.
All right, Section 4, real-world primitive mapping. Get ready, because this is your engineering cheat sheet.
Let's look closely at how these map over. An EVM storage slot, that simply becomes a single Solana account containing a serialized struct. A standard EVM mapping turns into either one massive packed account or multiple individual program-derived addresses. Dynamic arrays translate over to linked accounts, and an Ethereum contract address maps out to an executable program combined with those PDAs for its owned data. As for EVM event logs, they map directly to program-emitted logs, occasionally using indexed accounts.
So let's actually look at this practically. Say you're porting an ERC20 tokens balances mapping. You've really got two choices here. Option 1, you shove all the user balances into one large, packed account. Sure, it mimics Ethereum, but it creates a massive single point of contention, basically a massive traffic jam. Option 2, you create per-user program-derived addresses, or PDAs. This is like a custom mailbox derived from the program itself, meant exclusively for that one user. The payoff? Thousands of users can trade simultaneously. The trade-off? You're going to pay more rent to manage all those extra accounts.
Section 5. Upgrades and migrations. How do we evolve our code once it's out there? So what happens when your decentralized code desperately needs a bug fix? Ethereum developers absolutely love upgradable proxies, right? Using delegate call to perform this implicit, in-place code swap while leaving that giant filing cabinet of storage completely untouched. Solana entirely rejects that model. It explicitly separates your executable logic from your data accounts. So to upgrade a data structure on Solana, you have to literally migrate that data to brand new accounts or transfer the ownership authority to a new program. It is uncompromisingly explicit every step of the way.
Finally, Section 6. Key heuristics. Let's distill this into some practical rules for the SVM.
When you are designing your cross-chain architectures, always label your primitives. Ask yourself, are they cabinet local, meaning they absolutely have to be grouped tightly into a single account struct because they require atomic updates? Or are they mailbox sharded, meaning they can be distributed into many user-specific accounts to achieve maximum parallel throughput? Building on Solana means you are constantly playing this balancing act between the risk of network contention and the actual cost of data growth.
So whenever you find yourself worrying about your dApp suddenly freezing up during a massive traffic spike, just ask yourself this one fundamental question. Are my operations bottlenecking on a single filing cabinet, or have I properly spread them across multiple mailboxes? Let me tell you, trying to update a single global leaderboard mapping on Solana every single second is a recipe for absolute disaster. You've got to shard it out, distribute the load, use the mailboxes.
Now that you truly understand the core differences between those opaque stored slots and these explicit serialized data buffers, you are totally ready for the next level. In our next explainer, we're going to use everything we built today to evaluate the concrete mathematical trade-offs around cost, concurrency, and atomic updates. Because knowing the mappings is just step 1. Optimizing for cost is step 2.
Before we wrap up, I'll leave you with a bit of a provocative thought. If Solana forces us to make our data ownership and sizing completely explicit, could porting to the SVM actually force us to become more intentional, organized developers overall? Something to chew on. This explainer was created by Forge College. Be sure to head over to forge.college to dive much deeper into these concepts and explore an amazing library of Web3 educational resources. Until next time, keep building, and whatever you do, remember to label your mailboxes.